You are a student doing homework, and you discover the office building you work in could collapse in a windstorm. You work on the 45th floor. Thousands of people enter the building every day, and no one tells you. Engineers confirm the building is in danger. They begin emergency repairs at night, in secret. Welders strengthen joints while you sleep, and a hurricane is approaching the coast. Evacuation plans are prepared, but never announced. You go to work, completely unaware, and the building is saved. You do not learn the truth for 20 years. 1978, Citicorp Center, Manhattan. 59 stories, 915 feet tall. One of the most innovative skyscrapers ever built. The building does not sit on a traditional foundation. It stands on 4 massive stilts, 9-story-tall columns at the corners. The design was revolutionary. It allowed a church to remain on the site. The building hovers above it. Architectural magazines praised the concept. Awards were given. The building became an icon. And then, Diane Hartley, a graduate student at Princeton, starts analyzing the building for a thesis. She studies the structural system. She runs calculations. And she notices something strange. The building's wind resistance seems inadequate. She writes to the chief structural engineer, William LeMessurier, one of the most respected engineers in the world. She explains her concerns, and LeMessurier reviews her work. He realizes she is correct, but the problem is worse than she knows. During construction, a cost-saving change was made. Critical joints were switched from welded to bolted. LeMessurier had approved it, but he had only calculated wind loads for perpendicular winds, winds hitting the building face on. He had not calculated for quartering winds, winds hitting the corners at a 45-degree angle. And quartering winds create much higher stress on the corner columns. The bolted joints cannot handle it. In a severe storm, the building could fail. It could topple. 59 stories crashing into Midtown Manhattan. LeMessurier does the math. A storm strong enough to cause failure has a statistical probability of occurring once in 16 years in New York. Not once in a century, not rare, likely. And Hurricane Ella is approaching the East Coast, a Category 3 storm tracking toward New York. This is the story of the Citicorp Center crisis. The student who found the flaw, the engineer who confirmed it, the secret repairs done while a hurricane approached, and the cover-up that lasted 2 decades.
The Citicorp Center project began in the early 1970s. Citibank wanted a new headquarters in Manhattan, a statement building, something innovative. The site was on Lexington Avenue and 53rd Street. But there was a problem. St. Peter's Lutheran Church occupied one corner of the block. The church refused to sell. It had been there since 1905. The congregation would not leave. Architects found a solution. Design a building that stands on stilts. Place the massive support columns at the midpoint of each side of the building instead of at the corners. This creates a cantilevered structure. The building overhangs the church. St. Peter's remains on the ground level beneath one corner of the tower. The church gets a new modern building as part of the deal, and Citibank gets its skyscraper. The architect was Hugh Stubbins. The structural engineer was William LeMessurier. LeMessurier was a legend, MIT educated, brilliant. He had designed structures all over the world. The Citicorp Center would be his masterpiece. The structural system was unlike anything built before. 4 massive columns, each 9 stories tall, each positioned at the center of a side wall instead of at the corners. The building's weight is transferred down these columns to the bedrock foundation. The tower itself uses a braced frame structural system. Diagonal braces run throughout the building. They provide rigidity. They resist wind loads. The braces are visible on the exterior. They create a distinctive chevron pattern. The building's top is angled at 45 degrees, a slanted roof originally intended for solar panels. The design is bold, modern. It becomes one of New York's most recognizable buildings. Construction began in 1974. The church was demolished and rebuilt as part of the tower's base. The massive stilts were erected. Steel framework rose story by story. The project attracted attention. Engineers came to study it. Students wrote papers about it. It was featured in textbooks, an example of innovative structural design. During construction, a change was made. The original design called for welded joints in the braced frame system. Welding creates continuous, strong connections. But the contractor requested a substitution, bolted joints instead of welded. Bolted joints are faster to install, easier to inspect, and cheaper. LeMessurier reviewed the request. He ran calculations for wind loads perpendicular to the building faces. The bolted joints were adequate for those loads. He approved the change. But LeMessurier did not calculate for quartering winds, winds hitting the building at 45-degree angle. Quartering winds create different stress patterns. They concentrate force at the corners. And because the Citicorp Center's support columns are at the midpoints of the sides, not the corners, quartering winds create torsional stress, twisting forces. The bolted joints were not designed for this, but no one realized it. The building was completed. It opened in 1977. Citibank moved in. Thousands of employees. Retail spaces opened on lower floors. Restaurants, shops. The building was occupied and operational. For a year, everything seemed fine. The building stood, it functioned, it was celebrated. And then Diane Hartley started her research.
The construction of Citicorp Center was a massive undertaking. The 4 support columns were the most critical elements. Each column had to transfer the entire weight of the building to the bedrock below. The columns were constructed first. Steel framework rose from deep foundations. Each column was 9 stories tall before the main tower structure began. The base of the building was open, designed to accommodate St. Peter's Church. Once the columns were in place, the tower structure began. Steel beams and diagonal braces were erected floor by floor. The braced frame system was essential. It provided lateral stability, prevented swaying in wind. The braces formed a chevron pattern on the building's exterior. They were not just decorative, they were structural, load-bearing, critical. The original design specified that joints in the braced frame system be welded. Welding creates a unified connection. The steel pieces become one. The joint is as strong as the surrounding material. But welding is time-consuming. It requires skilled labor. Inspection can be difficult. The contractor, Bethlehem Steel, preferred bolted joints. Bolts are faster, easier to install, easier to inspect, and they had been used successfully in many buildings. LeMessurier was asked to approve the substitution. He reviewed the structural calculations. He analyzed wind loads. But his analysis focused on perpendicular winds, winds hitting the building on the flat faces. For those conditions, bolted joints were adequate. The building code required only perpendicular wind analysis. LeMessurier approved the change. Construction continued with bolted joints. No one calculated the effect of quartering winds, winds hitting the building at an angle. Quartering winds create higher stresses at the corners of a building. For most skyscrapers, this is not a major issue. The support columns are at the corners. They are designed to handle corner loads. But
But Citicorp Center's columns were at the midpoints of the sides. The corners were cantilevered, unsupported. Quartering winds would create torsional forces, twisting. The bolted joints might not be strong enough. The building was completed in 1977. It opened to great acclaim. The design was praised. The engineering was celebrated. LeMessurier received awards. The building became a landmark. And for a year, no one questioned the structural integrity. But in the world of engineering, assumptions are dangerous. The assumption that perpendicular wind loads were the only critical case was wrong, and it took a college student to notice.
1978. Diane Hartley is a graduate student at Princeton University. She is studying architecture. For her thesis, she decides to analyze the Citicorp Center. The innovative design fascinates her. She obtains blueprints, she studies the structural system, and she begins running calculations. Hartley focuses on the building's unique support system, 4 columns at the midpoints instead of the corners. She analyzes wind loads, and she notices something. The building seems vulnerable to quartering winds hitting at a 45-degree angle. She calculates the forces, and they seem higher than the structure can handle. She is not certain. She is a student, but the numbers concern her. Hartley writes a letter to William LeMessurier. She explains her analysis. She asks if her concerns are valid. She is respectful, cautious. She is questioning one of the world's leading structural engineers, but she wants to understand. LeMessurier receives the letter, and at first he is not worried. Students often misunderstand complex structural systems. He assumes Hartley made an error. But LeMessurier is thorough. He decides to review her work. He pulls out the Citicorp Center calculations, he looks at the wind load analysis, and he realizes something. He had only calculated for perpendicular winds. He had not analyzed quartering winds. He runs the numbers, and his blood runs cold. Quartering winds create significantly higher stresses on the corner braces. The bolted joints, which he had approved as a cost-saving measure, are not strong enough. In a severe storm, the joints could fail. The braces would buckle, the building would lose structural stability. It could collapse. 59 stories, 915 feet, crashing into one of the most densely populated areas of Manhattan. LeMessurier calculates the probability. How often does a storm with winds strong enough to cause failure occur in New York? The answer terrifies him. Once in 16 years, not a rare event, a statistical likelihood. And meteorologists are tracking Hurricane Ella, a Category 3 storm in the Atlantic. It is moving toward the East Coast, potentially toward New York. LeMessurier makes a decision. He will not hide this. He contacts Citibank. He contacts the building's owners. He explains the situation. The building is in danger. Repairs must be made immediately, and they must be done in secret. If the public learns that a major Manhattan skyscraper could collapse in a storm, panic will ensue. Evacuations could cause chaos. Lawsuits would be catastrophic. The repairs must be done quietly.
Citibank agrees. The building owners agree. A plan is developed. Welders will strengthen the bolted joints. They will add steel plates, reinforce the connections, make them as strong as if they had been welded originally. But the work must be done at night, after business hours. Workers and tenants cannot know.
The building will remain open during the day. Repairs will happen in darkness. The welding crews begin work in August 1978. They work from midnight to sunrise. They move through the building floor by floor, strengthening joints, adding reinforcement. The work is slow, painstaking, and Hurricane Ella is approaching. Weather models show it could hit New York within days. If the storm arrives before repairs are complete, the building must be evacuated. Emergency plans are drawn up. Red Cross shelters are identified. Evacuation routes are mapped. But nothing is announced. The public is not told. LeMessurier monitors the hurricane's path. Every update, every forecast. The storm is massive. Winds over 115 miles per hour. If it hits New York directly, even with partial repairs, the building might not survive. He calculates probabilities. He reviews structural models. He barely sleeps. And then Hurricane Ella turns. It curves away from the coast. It weakens. It dissipates over the Atlantic. New York is spared. The welding crews continue their work. By late September, the repairs are complete. Every critical joint has been reinforced. The building is now stronger than originally designed. It can withstand quartering winds far exceeding code requirements. The crisis is over. But the cover-up continues. Citibank does not announce what happened. The building owners stay silent. LeMessurier does not publish a paper. No press release is issued. The workers who did the welding are told it is routine maintenance. Tenants are not informed. The thousands of people who enter the building every day never learn how close they came to disaster. The secret is buried. For 17 years, the Citicorp Center crisis remains hidden. LeMessurier carries the weight. He knows what happened. He knows how close the city came to catastrophe. But he does not speak publicly. Then, in 1995, a journalist begins investigating. Joe Morgenstern writes an article for The New Yorker. He interviews LeMessurier. He uncovers documents. He tells the story. And the world finally learns the truth. The repairs to Citicorp Center were completed in late 1978. The building was saved. The strengthened joints could now handle quartering winds far beyond code requirements. The building was structurally sound, safer than it had ever been. But the cost was not just financial. It was reputational, psychological, and ethical. William LeMessurier's response to the crisis became a case study in engineering ethics. When he discovered the flaw, he did not hide it. He did not blame others. He took responsibility. He notified the building owners. He worked to fix the problem. His honesty likely saved lives. If he had remained silent, the building could have failed in a future storm. Hundreds or thousands could have perished. But the decision to keep the repairs secret was controversial. The public was never informed. Workers continued entering the building while emergency repairs were underway. Evacuation plans were prepared but never executed. If Hurricane Ella had hit New York, would the evacuation have happened in time? Would people have been warned? These questions remain unanswered. LeMessurier later said he struggled with the decision. He believed informing the public would cause panic, that chaos could be more dangerous than the risk itself. But critics argue the public had a right to know, that transparency is essential, that people should have been allowed to make their own decisions about the risk. The engineering community debated the case for years. Some praised LeMessurier for his integrity, for confronting the problem rather than hiding it. Others criticized the secrecy, the lack of disclosure, the paternalistic decision to manage the risk without public input. The case is still taught in engineering ethics courses. It raises fundamental questions. What is an engineer's responsibility when a flaw is discovered? To whom do they owe loyalty? The client? The public? The profession? The Citicorp Center remains standing today. It has been renamed. It is now known as 601 Lexington Avenue. The building has withstood numerous storms since 1978. It has performed flawlessly. The repairs worked. The building is safe. But the story of the crisis remains a reminder, a warning that even the best engineers can make mistakes, that assumptions can be deadly, and that vigilance is essential.
The Citicorp Center crisis changed how the engineering profession thinks about design review and peer analysis. Before 1978, it was uncommon for structural designs to receive independent third-party review. Engineers trusted their own calculations. Clients trusted the engineers. But Citicorp proved that even brilliant engineers can overlook critical factors. Quartering wins were not a new concept, but they were not standard in structural analysis at the time. After Citicorp, they became standard. Building codes were updated. Wind load analysis now requires evaluation of multiple wind directions. Quartering winds must be considered. The change was directly influenced by the Citicorp case. The crisis also highlighted the importance of communication between designers and contractors. The switch from welded to bolted joints was approved by LeMessurier, but it was not fully analyzed for all load conditions. Better communication, more thorough review could have prevented the problem. Modern engineering practice emphasizes documentation, review, transparency. Lessons learned from Citicorp. The crisis also raised questions about public disclosure. When is it appropriate to keep information secret? When does the public have a right to know about risks? These questions remain debated. In the age of social media and instant communication, keeping a crisis like Citicorp's secret would be nearly impossible today. But in 1978, it was possible, and the decision was made, for better or worse. Diane Hartley, the student that started it all, did not pursue a career in structural engineering, but her contribution was monumental. Her curiosity, her willingness to question authority, her careful analysis. She likely saved lives. LeMessurier credited her publicly. He called her work important. He acknowledged that she identified something he had missed. It is a testament to the value of fresh perspectives, of questioning assumptions, of rigorous analysis. The Citicorp Center stands today as one of New York's iconic buildings. Tourists photograph it, workers fill it. The building functions perfectly. But beneath the surface is a hidden history, a crisis averted, a disaster prevented, and a lesson for every engineer, that the stakes are high, that lives depend on calculations, that humility and honesty are as important as technical skill. The Citicorp Center crisis of 1978 was a disaster that never happened. A college student discovered a flaw that professional engineers missed. The building could have collapsed in a strong storm. Emergency repairs were done in secret while Hurricane Ella approached. Thousands of people continued working in the building, unaware of the danger. The crisis remained hidden for 17 years, and when the truth finally emerged, it changed engineering practice forever. William LeMessurier's decision to confront the problem rather than hide it likely saved lives. His honesty set a standard for professional ethics, but the decision to keep the repair secret remains controversial. The public was never warned. Evacuation plans were prepared, but never announced. The building was saved, but questions about transparency and responsibility linger. If you want to uncover more stories of American infrastructure hiding dark secrets, subscribe to Hidden America. Next time, we will explore the St. Francis Dam collapse in California, where William Mulholland's dam failed catastrophically just 2 years after completion, unleashing a wall of water that traveled 54 miles to the Pacific Ocean and left over 400 people gone.
We will investigate the ignored warnings, the unstable rock, and why Mulholland took full responsibility but faced no charges. Subscribe now for more hidden infrastructure stories. And remember, the Citicorp Center taught the engineering world that even the best can make mistakes, and that a student doing homework can save a city.